the AVR timer counter 0. So, it has got it is a 8-bit timer, and also the if the clock source is external. So, it will act as a counter, and the very important feature that it has is that there is an output compare match. So, basically when the timer is operating or the counter is operating, so you can have some intermediary values at which you want to determine a match. For example, if I have got say two activities E1 and E2 to be E1 and E2 scheduled. So, this and what we want is that this E1 and E2 they should be created, say this one after say 10 second and this one after 20 second. So, in normal 8051 type of operation, so what you have to do is you have to use two different timers, and then one for 10 second, another for 20 second, and accordingly generate two events and get the overflows detected and schedule those events. However, in case of AVR microcontroller, so this feature is there where we have got another register which is called output compare match, so output compare register OCR. So, in this OCR, so you can load these values say 10 initially, so that and start the timer. So, this timer when it goes up to 10, so it will this TCNT 0, so this will match with this OCR 0, and accordingly this OC 0 output. So, this output will be made 1. So, you get that information that this is the time for activate activate the action E1. After and then you can reload this OCR 0 with the value 20. So, that again when the count reaches 20, so you will get another match, and then you can start the activity E2. So, this way this is useful because I can have multiple activities started at different times which are controlled by the same timer. Okay. So, that is the feature with this TCNT this TCNT and 0 register and this OCR 0 register. Another timer that we have is a 16-bit timer. So, 16-bit timer is that a timer counter 1. So, that is a 16-bit timer. So, it has got dual comparators A and B. There are two output comparators A and B. Again this is up counter. So, if in previous example we have got only a single comparator. Okay. So, the OCR 0 was there, but here I have got two comparators A and B. So, otherwise it is same, it is up counter. So, interrupt on overflow, that feature is there, comparison with A and B OCR registers. So, that is there, and this input capture of external events is on the ICP pin. So, the ICP pin, so you can capture these external events, accordingly you can load it. It can also act as pulse width modulation facilities can be provided. So, 8, 9 or 10 bit pulse width modulation with up down counter. So, this AVR this counter 1 can also be modeled as PWM. So, we will see that slowly. Then this input capture unit captures the external events and gives them a time stamp indicating their time of occurrence. So, when that external event has occurred, so that time will be captured there. The external event signal indicating an event or multiple events can be applied via the ICP1 pin, or it can be via this AD converter, analog to digital converter. So, the analog comparator module can be used for doing that purpose. This time stamp we can note down the we can use it for calculating frequency, duty cycle. So, as I was telling in the last class that you can capture two different points of a signal, and accordingly you can determine say the frequency of the signal, or you can determine the duty cycle of the signal. So, those type of application can be done. It can also be used for creating a log of events, like when say if I say that I am counting the items coming on conveyor belt, and I also want to take a note like when individual items actually came to the point. So, that way I can do this by noting down the corresponding time stamps. So, AVR 1 timer 1, it has got two compare outputs, OCR 1A and OCR 1B. So, they are 16-bit registers because the timer itself, timer 1 itself is 16-bit. So, these are also 16-bit registers. The value of OCR 1 and OCR B matches with that of timer 1. User defined action will take place on this OC1A and OC1B pin. So, the actions are set, clear or invert. So, you can program it like this, that when this match occurs. So, the particular pin will be set, it will be cleared or it will be inverted. So, or another activity can be an interrupt can be made to generate. So, you can tell the processor that when this timer comes to this particular set value in the set in the OC register. So, you can it will trigger an interrupt. So, or the timer 1 can be cleared to 0. So, that is also another activity. Once set up, this output compares output continually without software intervention. So, you just program it once and from that point onwards it continues. It is good for precise recurring timing, like if you have to do some event in a periodic way after some periodic intervals of time. So, you can do this operation. So, you can take help of this timer 1 and load this OCR 1A or 1B register accordingly. So, that at periodic intervals, so you get an indication that this is the time to do that periodic operation. Frequency or tone generation, so different sounds you want to generate at various points of time. So, that can be done, and digital signal generation for infrared communication, software driven serial ports, for that type of application also. So, you can generate the control signal. So, particularly when you have to develop some handshaking signals at periodic intervals or at some fixed time points. So, you can do that using these timers. So, timer 1 can also be used for pulse width modulation. So, what is pulse width modulation? So, this is the diagram that shows how is it occurring. You see that suppose this is a triangular wave and there are two values. One is the low value of the pulse. It is basically, and so we set a value. So, when this signal goes below this point, when this triangular wave goes below this set value, we generate a high pulse. So, this signal makes a transition from low to high. So, at this point the signal is going below the set value. So, it is generating, it is becoming high. Now, after some time the signal will again rising and it crosses the crosses the triangular this set value again. So, at this point the signal goes low. So, you see that if I set that this as the comparator value, then whenever signal is higher than this, the value of the output is 0, and whenever the this triangular wave value is less than this set value, the value of the output is 1. So, you get a pulse like this. Now, if you change this DC level, if you change this DC level, so you can have different pulse width. Like for example, here suppose at this point we have changed the DC level from this one to this one. So, when we change this accordingly, so that cutoff will occur. So, this low to high transition will occur when the pulse is at when the triangular wave is at this point, and similarly this will go low when the triangular wave is at this point. So, this way we can have this pulse width modulated output. So, this is useful for driving motors, okay, or say the glowing LED. So, if you have to generate, but many times for communication also this pulse width modulation is necessary. So, whenever you need this sort of thing, so you can change the carrier signal feature. So, based on the base signal, so here the dotted line is the base signal. So, that changes the carrier signal features. When the carrier is crossing this, then we are generating a pulse of larger width when the base value is the compare value is higher. So, this is it has got two channels of this pulse width modulation output on OCR 1A and OCR 1B. So, that is useful for many applications. So, this particular facility we do not have in other microcontrollers like say 8051. So, timing control. So, we have seen that there is a timer 0 register, there is a timer 1 register. So, timer 0 register has got a control register TCCR 0 for clock selection, which is external clock or internal clock. Then there can be a pre-scaler, that is from which point it will start. Then timer counter 0. So, this is the this will hold the counter value. So, these are the two registers relevant for timer 0. For timer 1, we have got control register TCCR 1A and 1B. There are two control registers. Similarly, we have got two count. So, count value is there TC and T1. So, this is the count value. So, you can have this input capture register ICR1, where the capturing input at some point. Then timer counter on output compare register A and B. So, this is OCR register was there for timer 0. So, here also we have got OCR 1A and OCR 1B. So, here we have got another register in timer 0 which is OCR 0. So, that is not written here explicitly. So, that is another register we had for this output comparator, output comparison. And then timer interrupt registers are there. So, both the timers they have got mask and flag registers. So, they are not detailed here, but you can mask those registers, you can put a mask for the corresponding interrupts. Okay. So, that can be useful, just like in 8051 we have seen, here also we can do that thing. So, this timer counter sources, one is the shut off mode where nothing has to be done, like this these are the control lines CS02, CS01 and CS00. So, if these bits are 000, that means it is stop and the timer counter will be is stopped. So, if the value is 001, then the operation will be at the normal clock of the microcontroller. So, the timer counter will operate at the normal clock of the microcontroller. Then 010 it will operate at clock by 8 frequency, 011 will be clock by 64 frequency. So, this way up to you see there are a good number of setting 8, 64, 256 and 1024, and of course, we have got the default one setting. So, the CPU frequency may be divided by these values, and accordingly it will be so at 8 megahertz. So, these are 1/8 microsecond, 1 microsecond, 8 microsecond. So, like that. So, you can change the clock that is fed to the timer counter by setting these CS0 bits. And we can also have this external source like say 110 and 111. So, these are for the external pin T0, one is falling edge, another is rising edge. So, if you are taking it from the outside world, the clock frequency is coming from outside world. So, this can be fed to the pin T0, and that will be either falling edge triggered or rising edge triggered. So, if you look into the interrupts, the interrupt handler, so it will halt so for any interrupt, this is true that it will halt normal code execution for doing something sensitive. So, we have got this interrupt handler. So, that interrupt service routine. So, here the name is interrupt handler. For interrupt vectors we have. Then the interrupts may be used for resetting, then timers, time critical code like that, or hardware signaling, like something happens in the hardware. So, that way you can signal that. So, there are external pins for feeding that interrupt. So, just like other interrupts. So, other processors we have this thing. So, this is the table that contains this interrupt vectors. So, vector number 0 is the reset. So, this is external pin, power on, reset, brown out reset. So, these are all they will come to this reset. Okay. There are so many points by which this reset can come. Then INT 0 and INT 1, these are two external interrupts. Okay. So, they are vector numbers and 2 and 3. Then this is timer counter 2 compare match, timer counter 2 overflow, timer counter 1 compare match. So, this way we have got all these timer counters overflow and the match interrupts. Okay. So, these are there. Then there are serial transfer complete, SPI, STC type of thing, then UART there are interrupts. So, the ADC there is an interrupt. So, this way we can have a number of interrupt sources, and in case of this AVR microcontroller. So, here it is there are 21 such vectored location from which at which the interrupts can land, and each location you see it has got 2 byte address. So, 000 and 001. So, they will hold the vector address for the reset. So, there should be the jump instruction that will be 2 byte wide, and that will hold the actual ISR address, just like other processors. So, everywhere you see that there is a gap of 2 bytes for holding the interrupt service routine address. Then we have the watchdog timer. So, this is the watchdog timer, it will be clocked from separate on chip oscillator running at 1 megahertz. So, it is so we can, so watchdog we know that if any of these events occur, then it will send this MCU reset. Okay. So, this so watchdog timer it overflows, in that case it will be coming to this reset, this output will be 1. Okay. So, this when the output is 1, so it will be sending a reset to the processor. So, this way this watchdog timer is useful when we have got some activity which was supposed to be complete within some time, but it is not. So, in that case, in those cases, so we can have these watchdog timers for doing this operation. So, this AVR microcontroller has got many interesting features, like say compared to 8051 or even ARM. So, we have got many interesting features, and they are that is why they are also quite a lot of usage you can find in different embedded applications.